properties that you would probably want out of a zero knowledge system, such as succinctness, wherein the verifier should run in time much lesser than actually running the whole computation. And also, you probably want zero knowledge, wherein the verifier does not learn anything about the underlying witness, the secret data, right? Right. So there are many, many applications of zero knowledge proofs, ZK snarks. So just leaving the snark part aside and focusing on the ZK part, right, wherein we actually want some of these privacy preserving properties, right, for ZK. So we have tons and tons of applications for that, starting with Zcash, of course. We have ZKML, private smart contracts, decentralized hidden information multiplayer games, and tons of other applications, right? But while trying to build all of these beautiful applications, we run into one bottleneck very quickly, and that is that proving is really slow, right? So, for example, trying to hash something of maybe 10 kilobytes of data maybe takes very few milliseconds to run it natively on your machine, but can take like over a minute based on your machine, right? If you're doing it naively for Groth 16. So so there are various ways that people have tried solving this. So again, the most naive way is like just delegate all of the proving part to like a AWS or a public cloud, right? And uh, that is one way in which people have tried solving this. And uh, there is this other paper which was called DZIC, and what people try to do here is use like a cluster, a Spark cluster kind of thing, and there you get good scalability. But then again, uh, with public cloud or when it comes to DZIC, right, you run into one problem, and uh, it's a big problem wherein you kind of end up leaking all your secret witness data to the worker nodes, right? So maybe the goal should be outsourcing the zero knowledge proof generation, but with privacy, right? So again, you would probably have two goals when you're trying to do something like this. So one is the efficiency part. So again, it's of no use if you're trying to outsource something and it runs slower than actually running it locally, right? So efficiency is definitely a very important piece of it. And again, you would want it to be private. You don't want your witness data to be leaked in the worker nodes, right? But unfortunately, today you can't use cryptographic primitives like fully homomorphic encryption because they're just too heavyweight. They're outsourcing it using FHE techniques will still be slower than running it natively in your machine, right? So one way that we are trying to solve this is using some sort of threshold privacy scheme. So we are using a lot of these MPC techniques to actually delegate the proof in a privacy preserving manner. So, right. So there is this concept of threshold privacy. And maybe who here has heard about threshold secret sharing, threshold signatures? I'm guessing everyone, right? So, yeah, can one of you maybe like in your own words define what threshold signatures or threshold secret sharing is? Can one of you probably like to explain what threshold privacy is? Threshold secret sharing.
I think threshold
Yeah.
signature or threshold privacy, you need like n out of n people to actually sign something for it to be actually signed. Or I guess in terms of threshold privacy, you need n people to approve decrypting something to actually being able to decrypt it.
Yeah.
N out of n.
Totally, yes. And this is something that's being used in a lot of MPC wallets as well today, wherein you kind of distribute the keys among multiple nodes, and n out of t have to be present for you to actually sign something. So again, this is one of the core pieces in MPC. It's called secret sharing, right? So there are many schemes to do secret sharing. So probably the most famous one is Shamir secret sharing that I'm sure many of you have heard of. So uh, here you actually try to represent the data using a polynomial, and you need n out of m to actually infer the final value. There is another scheme also called as additive secret sharing, wherein you would need all the parties to come together, right? Unlike Shamir's secret sharing, right? So yeah. So again, we try to these are our two North Star metrics, trying to go for maximum efficiency and also hit a lot of these threshold privacy goals. So as long as we have less than more than T honest nodes in the network who are non-colluding, we should be good. We should be able to create this using a certain amount of privacy guarantees. All right. So maybe I can very quickly give a whirlwind overview of what multi-party computation looks like. So what is MPC? So MPC is a way in which multiple parties can come together. These parties are disjoint and sometimes untrusting of each other. They can come together with their private data and jointly compute something such that no other party learns anything about the other party's hidden information, but they can jointly get the result together, right? Uh, so this is a core primitive that we are trying to use in our application, right? So there are few pieces in MPC. So just like ZK Snarks, MPC also has these arithmetic circuits internally. And there is this very important component in MPC, again, which I just highlighted a few minutes back, which is secret sharing, wherein you have a data, you split that across multiple chunks. And if you want to get the share back, you kind of need all of these chunks to come together to get the final result, right? And again, there are few important properties of these secret sharing schemes such that you can easily add local shares together. So you can perform additive operations, affine operations on these secret shares such that when you get the message at the end, it's almost like you did these operations on the private data. But multiplication is the key sticking point in a lot of MPC schemes. Addition is easy, but multiplication is always difficult. And the depth of your circuit or the circuit complexity is usually measured in how many multiplicative gates you have in the MPC circuit, right? All right. So like the most basic technique would be to use a generic out of the box MPC solution, just throw that onto a snark and see if we get good performance gains. But unfortunately, that doesn't end up working. There are tons and tons of flaws that I wouldn't say flaws, but there are a lot of uh, there are a lot of sticking points in the way snarks are designed usually, such that a generic MPC tool doesn't really end up working. So one problem is that you have to kind of uh, work with two different finite fields. So the prover and verifier uh, uh, are running on two different finite fields. So you kind of have to reason about that. And secondly, snarks, right? They have two important components underneath. One is the PIOP and the other one is polynomial commitments. So both of these are like very heavyweight cryptographic primitives, and representing that directly into MPC is very expensive. So you can't directly throw a MPC generic MPC algorithm to a snark. You kind of have to do this a little more intelligently. Right. So just to give all of you a very quick recap of the modern day snarks, right? So something like Plonk internally has these two primitives, PIOP and polynomial commitments, right? So you start off with your data, you create a polynomial out of that, you create a polynomial commitment and send that over to the verifier in the PIOP protocol. the verifier sends a random oracle challenge back to the prover, and you continue this for several rounds until you go to the final round, wherein you try to evaluate over certain query set and send the final evaluation proof back to the verifier, right? So this is like a whole whirlwind overview of how ZK snarks work today, right? Right. So I kind of mentioned two problems with directly throwing a MPC solution to the snark. So one is there are multiple different components in a snark, which is the PIOP and polynomial commitment. So stitching that together is a problem in MPC. So let's see how we can tackle the first problem. Also, the second problem is these operation in itself are quite expensive, right? The PIOP and the polynomial commitments are quite expensive. So we'll be going over how we solve that part as well. So we'll do a very quick summary of how we solve the first part. Right. So if you take a look at the PIOP, right, the interactive oracle proofs, you can probably summarize the operations in these 5 steps. So every polynomial IOP kind of does these no, 6 steps actually. So you usually evaluate your polynomial over some subgroup or evaluation domain, if that's a better word for you. You divide a polynomial with another polynomial. You kind of do addition operations, these affine operations, right? Interpolation operations. But the good thing about all of these 5 operations is that these are linear operations, that these can be done directly on a machine. These do not involve any kind of interactions among the nodes in the multi-party MPC protocol. All of these can be done locally. But the only problem is with when you try to multiply 2 polynomials together, right? So uh, in these MPC protocols, we have additive homomorphism, but we do not have multiplicative homomorphism. So multiplying 2 polynomials together is a bit of a problem. So uh, in our protocol, right, what we try to do is we, before beginning the whole MPC rounds, we kind of have a pre-processing step wherein each node gets some amount of randomness, and there is this concept in MPC called beaver multiplication. So we are kind of using that concept here to speed up polynomial multiplication, right? Right. And then coming to the second part of the puzzle, wherein the second part of the puzzle was trying to speed up the polynomial commitments also now, right? So, uh, right. So let's take KZG, for example, the most famous polynomial commitment scheme maybe, right? So there are 2 steps in the KZG polynomial commitment scheme. One is the actual commitment part, and secondly, we are opening the commitment, right? So during the commitment part, right, we are doing a simple multi-scalar multiplication, right? This one, we have some scalar values, and uh, we have these SRS parameters over which we want to build the commitment. And the again, the beauty of this is that the whole commitment scheme is additively homomorphic, right? So every single node can create the commitment locally, and eventually all of those commitments can be collected together, and you can use that to build the final commitment, right? So just like a standard KZG protocol, every single node in the MPC protocol calculates the commitment locally. They come together at the end to generate the final commitment. And after creating the commitment, you kind of have to open the commitment and prove that the evaluation also happened correctly for a point on the polynomial, right? On the secret shared polynomial. So again, even this step is linear. Every single node can kind of calculate the witness polynomial and create an evaluation proof at the end locally, just the way we did it here. So yeah, uh, uh, doing this with KZG or bulletproofs or IPAs is very simple. We can come to Fries. Fries is a bit difficult right now to do this because it doesn't have additive homomorphic properties, right? All right. Okay, so I think I've been talking a lot about theory and polynomials and all this garbage, but coming to the most important question, does this actually result in any kind of concrete performance improvements, right? Does this actually make the whole protocol fast end to end, right? And the answer is thankfully yes. Right. So, by the way, this is inspired by tons and tons of papers. So we have used the paper starting with collaborative snarks by Dan Bunet, and then there was this other paper called EOS and ZK which came out of Berkeley, and we have used a lot of the concepts from all of these papers, right? And these are some metrics that we reproduced from their papers while trying to build our own implementation, right? So if you try to, so these are some tests that we ran, right? Comparing, generating a proofs locally, which is the orange line, and creating a proof using the MPC protocol that we have created, right? So you can see that we have like order of magnitude improvement, right? We almost see 20x improvement when we try to do it locally versus use our MPC based delegation. And this graph is for the Groth 16 protocol. This one is for Plonk. And you can see in Groth, most of the time is taken in the MSM steps, right? Almost 90% is the red part is for MSM, the yellow part is for FFTs, right? So almost majority of the computation is just the MSM bit. And the beauty of MSM is that you can parallelize this a lot. You can split it very easily, but that's not the case with FFTs. FFTs is not the most friendly parallelizable algorithm, right? So Plonk has a lot more FFTs compared to Groth 16, right? But we still see some improvement. And then, yeah, I'm sure some of you have this question. So evaluating, getting some metrics by changing the bandwidth, right? So MPC again has a lot of communication happening between each nodes, and ideally we would want that communication to be as quick as possible, right? So again, just to explain this quickly, so this blue dotted line is theoretically the maximum limit that we can reach, right? If we split it and the kind of properties that we want, this is the theoretical optimal. And if you see, the green line indicates when you have 4 Gbps connection between all the nodes, right? Which is something that you can probably get in a data center. So you kind of can get to the optimal limit, but once you start going down, so let's say you have 64 Mbps bandwidth between all the nodes, then the performance starts degrading really badly. So ideally, you would want at certain point the limiting factor is not compute, it becomes the bandwidth among all the nodes. So you'd want the latency to be reduced and also bandwidth as high as possible. Yes, so we have few things that we want to implement in the coming few months. So so right now we have something called as semi-honest security in our setting, which basically means that no single nodes learn anything about the private data of the other node, but there is this chance of a node trying to corrupt the data and trying to malleate the input, which means that he can try creating, he can try messing with the final MPC result, right? So we kind of want to avoid that, and that is something called as malicious security in MPC, wherein you get protection against these kind of tampering of the data by the nodes as well. So we have seen few papers trying to solve this. So we are trying to think how can we approach that, and yeah, we are trying to optimize a lot of things. So there are few things wherein you actually don't need MPC, that those things can be some things are witness independent, so you don't really want to throw MPC tools at the witness independent part of the data. And yeah, we want there are some other challenges in just optimizing the code, the algorithms part of it that we're trying to address. Right. So you can take a look at our GitHub repo. We have built a lot of these primitives for the Halo 2 ecosystem. We have built the distributed FFTs, the distributed MSMs in MPC setting. And we're trying to do the same for the ArcWorks backend as well. So ideally, you will be able to create a Groth 16 proof end-to-end on the ArcWorks backend using our framework very soon. And yes, with that, I come to the end of my slideshow. Thanks, everyone.
First question.
Yeah, please.
So if one node is semi-honest, right? So assumption is semi-honest. So if the node want to maliciously modify the data or invalidate the partial witness, so in the end they will get invalid proof.
Yes.
But it's still a denial of service attack, right?
That's a good question. Yes. So if that is a bad node, he would not be able to create fraud proofs at the end. So you're not breaking the soundness guarantees of zero knowledge proofs. But there is this factor of denial of proofs, denial of service that can happen. A node can keep entering junk data and kind of stall the whole MPC process, right? So you can have some sort of timers in place, some sort of reputation system in place, some sort of staking mechanism potentially, wherein if you behave dishonestly, you're slashed. So we are thinking of those solutions.
But here is the problem. So you have to identify the dishonest part, the node, right? So it's really hard to do it because their knowledge is particle.
Right. Right. Yes. We can. Yeah, I'd love to talk about this with you, but do you think we can use some sort of ZK proofs? Each node can use zero knowledge proof saying that they're behaving honestly.
Yeah, we have to discuss about.
Yeah,
it's not easy. So
yeah, even we are kind of figuring this stuff out. Right, but if you change the protocol from semi-honest to malicious security, I feel like the MPC will probably take care of a lot of these things, right?
For sure.
Yeah.
But actually, the use of zero knowledge proof underneath.
Right. Yes.
But I think probably an optimized version will be add a little bit zero knowledge proof to solve it.
Right.
Instead of use a malicious version.
Yeah. We were looking at some metrics around doing that. There is this MPC protocol called as speeds, but that kind of gives you 2x more slowness if you introduce the malicious security now in MPC. Yeah. Maybe eventually we can have some sort of trade-off for the client side. So we can ask the client, do you want full-blown security? How much security do you want? Are you okay with 50% of the nodes being honest, or do you want 100% of them?
More of a basic question, but
sure.
Like, how is let's take like Shamir sharing, like how is the malicious security guarantee like kind of maintained there? Like, let's say I just start throwing out like random numbers as key shares. They don't put any polynomial, like it's also a denial service test, or like I'm just kind of wondering.
Right. So a lot of these MPC wallets, right, that use Shamir secret sharing, they have malicious security. So even though you try to enter junk data, there are kind of checks against that.
Doesn't it also, like, let's say that I guess there's redundancy, so there's always someone else that can help with the key share. But yeah, I guess in that case, like kind of fail mechanism or like, I guess probably depends on the exact protocol. Like there has to be some mechanism by which. Well, first you have to authorize the node to share the key share, and then if they start junk data, then you have to kind of authorize a backup or something. Like how does it work?
Right. Yes. If I recall correctly, as long as T shares are fine and the other ones are invalid, it should still go through.
Oh, okay, everyone signed all of them. Yeah.
Yes. Right. Right.
I guess I was thinking more about the recovery. Like I usually see FTC is just like usually in the context of like recovery, so there kind of an authentication process involved in reconstructing the feature. Yeah, that makes sense.
Yes.
So the reason for using an MPC is to make sure you don't take your witness to an external server, right? That's
right. Yes.
So, like, in which part of the protocol do you actually need to aggregate these different shares between the different MPC providers? Like, do you still need to aggregate this in order to do the proving?
Aggregate what?
Like in the proving, like how do you actually prove between these different MPC providers?
So I did not get the full question.
Okay, I guess like to put it another way, like you try to get this like privacy of the witness by splitting it across like different MPC providers.
Right.
Does it at any point in the protocol that you need to get these shares from different providers and put them together in order to reconstruct it? So at which part of the protocol do you actually do the reconstruction and
right? Okay, that's a good question actually. So the delegator, right, the one who's actually interested in creating the proof, right? So let's say you want to create a proof for yourself, right? So you have the secret data with you right now, and you create the secret shares in your machine and you throw that to different nodes in the network, right? So the nodes do some operations locally, and it's okay for all of those operations to go to one single node in the network, right? So let's say each node builds a share of the commitment. It's okay for all the nodes to send that commitment to one single node in the network. So that one single node is kind of doing the part of actually collecting and I mean, yeah.
And what is actually sent to one the single? What is actually sent to that single? Like you say the commitment, like commitment of what?
So if you're trying to build a KZG commitment, let's say out of a polynomial, right? So each node kind of, so each node runs a MSM protocol locally in the machine, right? Creates a share of the commitment locally and sends all of those shares of the commitment to one single node. And that one single node joins all of those shares of the commitments together. And since these shares are additively homomorphic, right, you can combine all of them together to get the final result. Yeah.
So at first, how to distribute the secret data?
Oh, right. So the client generates the witness locally, the extended witness. All of that happens out of the MPC protocol. That happens locally in the client side, and the client side has an encoding process wherein he actually creates the shares. So it's the delegator who's actually creating the shares and sending that to the network, basically. Does that make sense?
If you mean that if you have 10 providers all at the same time, your client side generate the data, and the data will divide to 10.
Right. Yes.
And tend to get different.
Exactly. Yes.
So
Yes.
client side need to maintain this provider needs.
Yeah.
Also, okay. And another question is that what kind of computation will be able to navigate this thing?
The computation can be done.
What kind of computation need to be outsourced to the
Right. So in a ZK process, I think there are two big primitives that we kind of try to solve. One is the MSM and the FFT, right? So both of those processes happens. So all of those computation happens in a MPC manner. So
many staff for these two.
correct, yes, MSM and entity, right? So we are not doing the witness generation in the MPC process. We are just doing the proving step in the MPC process. Yeah. The witness generation happens on the client side, which is just field operations. These are not expensive cryptographic operations. Those happen really quickly. The proving part, all of that happens in a distributed manner. Yeah. So we kind of want to get both the benefits. We want to get the privacy preserving part as well, and we want to do it efficiently as well. So we're kind of trying to marrying the ideas of DZK paper, which is trying to run all of these in a Spark cluster, right? Trying to distribute it together naively. But yeah, we're trying to like have best of both worlds, fast and privacy preserving now.
In the graph, you were showing like the comparison between proving on the client and proving like the MPC server, right? Like, are they the same machines or like all the machines in the MPC kind of server, are they similar to the client, or is it like?
Oh no. It was a MacBook Pro actually, like a basic MacBook Air machine. Sorry, not MacBook Pro, MacBook Air M1.
That was the client, right?
That was the client trying to run it locally.
And the server would be like any AWS server.
So yeah. Yeah, that's a good question. Actually, the nodes are not all homogeneous. It's not the same nodes. There is one master node which has a lot of memory and a lot of cores, right? So so we need one big machine, and all the other machines in the network can be commodity machines. They can have 2 gigs of RAM, 1 core memory. These can be tiny machines, right? Yeah. You need basically one giant machine. A GPU will be ideal, and all the other ones can be smaller CPU machines.
But is this how like every MPC protocol works, or is this like, or is this something specific to what you're doing? Like there has to be some like master node and
right.
Child node or whatever.
Yeah. No. This is not usually how MPC works. We kind of have to do it this way because of the FFT operation. That's the only reason we have to do it this way, because in FFT, right, you can't parallelize the whole algorithm, right? You actually need a lot of memory, right? So FFT is a recursive algorithm, but at one point you reach a step wherein you need a lot of random access in the memory. So yeah, one part of the step needs this locality of information. So just because of that, you need a big machine. It'll be good to see if we can incorporate this in other protocols like Hyperplonk, which does not need FFT, right?
Yes.
I feel like there we can eliminate this big machines concept. Everything can be like a very tiny machine, 2 gig RAM, like having hundreds of them.
Yeah.
Yeah.
So FFT as an algorithm cannot be split. Like if you have a big polynomial, you have to do the FFT in a single machine. Like, is that the case?
Yes, I think yesterday in Go Ignite Mass talk also talked about that.
Yeah.
Right. Any other questions?
Like maybe try the some check based.
Oh yeah, we want to try that. Yes, on the list. Yeah, we are kind of still figuring out how can we solve the fry part, because we kind of can't implement stacks right now directly into this. That is a big challenge. If that can be done or not.
So only additive homomorphic can be done like that. Say.
Yes, in the current way, or the state of the art research that's been going around, people still haven't figured out way to do stacks efficiently using MPC. Yeah, again, I don't want to take credit for any of the theory or the research. All of this has come out of most of the universities in the last 1 or 2 years, right? So we are mostly doing the engineering implementation part of it. Cool, I think.